combinations of diamine and dianhydride, you can in fact tailor the pore size distribution with a most probable pore size of 50 nanometer to 30 nanometer or so. Okay? So chemistry helps us, and making chains stiffer, we can get narrow pore size. Making chains a little bit more flexible, we can open up the pore size. But that doesn't solve the problem completely. So you know, we had to we had to look at even the effect of solvents. So right now, this is a part of physical chemistry that we all learned, that every amine would undergo dissociation. It has its you know, pKb values, and every dianhydride would undergo hydrolysis, making diacid, which would undergo dissociation, its pKa value, and that pKa and pKb value are very much dependent on the solvent. Okay? So the solvent system that we have for polyamide system is dimethyl formamide, dimethyl acetamide, and we can make different combinations of that to get you know, the pKa and pKb values, so that gelation becomes faster or slower, and as a result our pore structures would open up or become very tight. And that's the you know, engineering that we already did, and so let me just present a couple of slides. So if the material is prepared only in 100% DMF, you get this kinds of tight knit structure, and then 100% N-methylpyrrolidone, little bit more open, 100% dimethyl acetamide, even more open. So structures are a little bit more uniquely defined to give us enough macropores for handling air. Okay? So that's something that we did, and they are also mechanically robust in the sense that they can take about you know, a strain of 1% and without failure, and their modulus is defined right here, high modulus. So it can handle the force that you have in handling the materials. Even you can cast, you can supercritically dry and roll it up, not a problem. Okay? Then the second example that I am going to talk to you about is drug delivery. The same mesoporous materials have drug delivery applications, but we do not want to do drug delivery with polyimide because it's not biocompatible. So then the material systems that we worked with is cellulose, and people who are familiar with cellulose, it's basically cotton, and you dissolve in a system to make a gel and then turn that into an aerogel. But what we wanted to do is the following, that not like a swallowable drug delivery, but well, many of us would use nasal spray. So I was approached by a pharmaceutical company about designing something where the drug would be loaded into a tiny 1 micrometer to 10 micrometer size particle, and we would put it in an alcohol suspension and then spray. It would go into the nasal canal and stay there and keep on delivering drug over a period of time, and then biodissolve and go away. And so that's why we thought about cellulose, and dissolving cellulose into a gel or turning that into a gel is not an easy task. You know, people have used sodium hydroxide, people have used ionic liquid, etc. So what we did is we used ionic liquid and dissolved cellulose into a gel, and then turned them into microparticles by capillary breakup. Basically, put it into an ethyl alcohol in a vessel, and the cellulose solution, and then basically break it with a stirrer so that tiny droplets are created. And those droplets are actually gel droplets, cellulose gel. Then we load drug on them, and then we again look at the loading profile and also drug delivery profile from them. So let me share with you how these particles are. You look at the scale bar here, 500 micrometer. There is a wide distribution because of the non-uniform shear distribution in the hydrodynamic breakup. And then we dry them. They are perfectly spherical with extremely porous surface area, and this scale bar is 10 micrometer, by the way. And if you look at it, 100 nanometer, they are porous, and inside structures are also porous. So these materials are very good host for drugs like antibiotic, and you can put it in, and they would release over a period of time. So we did that, and we got slower drug release percentage, and we studied the kinetics of it. It's nice kinetics for us. Then we wanted to make these kinds of, or convert these kinds of materials into core cell particles or porous particles, like what we just did, and then core cell micro rods, where the shell itself is going to be an aerogel with 90+% porosity and mostly mesopores. And why are we interested in this is these kinds of materials are going to offer transport barrier of a liquid or some kind of active material that we can enclose, and the transport would be mediated because of the porosity and diffusion through the pores. But making this is not an easy task. People have made core cell particles with solid shell, but 90% porosity is not easy. So that's why we went for microfluidics, and also like this. So the pore size are 10 to 200 nanometer, and then polymer strand diameter is about 50 nanometer. So now I'm playing a video of a system of a microparticle that we created from syndiotic polystyrene, like the polystyrene foam cup that we drink coffee or hot beverage from. These are all atactic polystyrene. Now there is a variation of polystyrene which is syndiotic, which is more pricey, and that material can undergo thermoreversible gelation. And so you can dissolve it in a solvent, hot solvent, and then as you cool down, the material turns into a gel. And so what we did is we converted that polymer solution into tiny droplets, and that droplet turned into a micrometer size particle like here. And so this micrometer size particle is then pushed to a water oil suspension. Okay? And syndiotic polystyrene being hydrophobic, it loves oil. So all the oil droplets are actually rushing to it, and it can pick up about 200,000% of its own weight, because it's 95% porosity and very little solid there is in this microparticle. So this would be a good example of guided cleaning of a noxious chemical which is stuck somewhere. You can in fact put a magnetic particle here, and with a magnet guide it to a location, and then it is going to absorb completely the liquid, and because of the capillarity, the suction would be very, very fast, and then you guide it out, and it's done. Cleaning job is done. Okay? So so the microparticles are created by in a system called microfluidic setup, and people who can spend money, you are welcome to spend money. But my student Nicolas Tio, he built this setup with only $2. Okay, so he bragged everywhere he gave a talk that I built a microfluidic setup for $2. So he got some needle, PVC tubing or Tygon tubing, and some PTFE tubing, put them together, your microfluidic setup is done. Okay? And so we wanted to create a gel particle out of polyimide system. So I have a video here, so let me play. So, so these are the polyimide sol that are being dropped from the microfluidic droplet generator into hot silicon oil, and as they turn into gel, they actually line up and then go up and then settle. So this is a continuous process through a system that we do, and we are able to make tons of microparticles out of polyimide, and you can implement this same technology for many other things. So a paper is out in Langmuir now on this, and also another paper is out in core cell regime. So we looked at the regime, but that's not important for the talk today, because I have few other things to share with you, and it is actually in the jetting regime, and so the next thing is to buy an expensive microfluidic droplet generator that would give you even tinier droplets. So at least the physics did not depend on the scale that we dealt with. So these are some of the SEM images of the particles that we created. These are the gel droplets. Then after supercritical drying, and you look at one of them, it has some pearl-like finish on the surface. Okay, so typical diameter is 200 micrometer. Now you can make it 1 micrometer, but then you have to deal with statics. Handling would be very difficult for that kind of particles. So core cell particle we created the same way with we extended another wing. Core liquid, a cell liquid gave us one droplet, another outer flow gave us another shell, and then we basically take it out. And we can in fact keep on adding to add layers in the droplet without any problem. Okay. So again, I mean, you break one of these particles and you see that you have a very nice shell, and shell thickness is less than 500 nanometer, and the shell itself is extremely porous, outer surface, inner surface, and this is the thickness. So it's a good transport limiting material, and there are some droplets that are even thicker than that, so you can also control the thickness to give different time scales for barrier diffusion. Okay, so let me take you to the last part of my presentation today, which is how can we make an apparel or a piece of aerogel sheet that we can cut and then put it in the face mask. So we have a process here. It's a roll-to-roll process in our department. Basically, we cast a gel right here. The gel would be cast with a doctor blade, and then it flows, and then we collect the material on a roll system, take it to a supercritical dryer, and so the kinetics of gelation, the dynamics of pore formation, and also the spreading, all three are very important. So we have very good handle on how to make sheets of material, and we are able to make it. So I just wanted to share with you that we have this process to make it to a commercial application. And now I want to know, I want you to know why we think these aerogel materials are good for filtering out airborne nanoparticles. So we all studied in physical chemistry a number called Knudsen number. So gas molecules collide with each other and then go to a distance before the next collision. That's the free path. And so there is a mean free path. And for air, like nitrogen and oxygen mixture at room temperature and atmospheric pressure, it's about 70 nanometer. So if you have a pore which is 50 nanometer and it's filled with air molecules, well, nitrogen and oxygen molecules are stuck. So the only way that transport of heat can happen through these materials is through thermal conduction, and thermal conductivity of air is low. That's why aerogel materials are good thermal insulators. So that's the largest market for aerogel materials as thermal insulation. But you can use the same dynamics where your large size pores would handle air and small size pores would take out the particles, airborne nanoparticles. Then it's a filter material. Okay. So we did that surface filtration, depth filtration. It's a basically the core discipline of chemical engineering or separation. So these airborne particles can be nanoparticles like carbon nanotube, or could be viruses, and we allow them to go through this filter material. Some of them would permeate through it but get stuck, and so the way we did this kind of testing, and these are the papers that we have published. We have been publishing since 2015. The first study on aerogel materials on filtering airborne nanoparticles. So this is the test aerogel with 90+% porosity, and this is where we keep it. Then there is O-ring, and our incident particles are airborne sodium chloride. We did not want to do this work with viruses. We are doing it separately. but the dynamics is the same. So this is a particle size distribution of sodium chloride. You can create it by atomizing a solution of sodium chloride in water, and then allow that, mix it with air, and then guide them to go through this filter material. And this is the support wear mesh, and there are particle counters above it and underneath, and then you look at what is the airflow flow rate. So you can also use Darcy's equation to find out the permeability. And what we found out is that commercial filters would have a permeability of about 10 to the minus 12 meters square. And our material is giving us about 10 to the minus 10 meters square. So it's about a factor of 100 higher rate than what you can get in commercial filter, because it's 90+% porous. And in terms of efficiency of particle taking or rather screening, so our efficiency approaches close to 100%. So these are all cake filtered sodium chloride nanoparticles that are captured within the material. And this is really the telltale example of how these materials can be used as filters. And so you can also monitor some of the particles that are inside the material, and they create kind of a fractal network structure like the pore architecture that we have. And so they are stuck, and we have close to 99.995% efficiency, and that's the efficiency, maximum efficiency of the filter tester, TSI filter tester that we used. So so now we want to increase airflow. One way to do that is to create something called aerogel foam. So we had aerogel, now create a foam-like structure through emulsion templating. And so these are some of the large pores through which air can flow, but there are these kinds of skin materials which are aerogel materials through which air has to go, but now this convection distance is shorter. As a result, the permeability goes up even factor of 10 higher than on the aerogel. And these materials also have 100% filtering efficiency of nanoparticles. So, so we did, and again, we cast these kinds of materials for making aerogel foams. So apart from gelation kinetics, pore formation, etc., emulsion stability is another issue here. So emulsion, because we are using emulsion templating in a sol, so we have a second liquid. That liquid can either sink or can go up, and as a result, it can create some gradient porosity, which is a nice feature for these kinds of applications. So, so we did, another work with this same aerogel material, but we do not turn them into aerogel. So we get the gel material, and basically we subject this to oil-water separation, especially. And so I read, and this may be your experience too. So in winter, we always use hand lotion or cold cream on our hand, okay? And basically these are emulsion, oil-water emulsion with stabilized by surfactant. And so skin can allow it to spread because it loves oil, and so tiny water droplets are going to be separated out. And these water droplets then take latent heat and go out or evaporate, and that's why we feel a little cool, okay? So the same concept we apply here. Our aerogel material is hydrophobic. So if we have different surfactants of different HLB values, people who are familiar with surfactant chemistry, there are HLB values, hydrophilic balance. These materials can adsorb, preferentially adsorb or take out the surfactant, just breaking the emulsion. And this is something that we are doing with 99% efficiency of removing water from ultra low sulfur diesel fuel, okay? And the same material I shared with you, we did virus experiment of flu viruses by, so one of my colleagues, Andy Baumann at Ohio State University, he's an associate professor in School of Veterinary Science. So he has a lot of sheep, and he cultivates them because these are the breeding grounds for viruses. And people who are familiar with the Wuhan outbreak of novel coronavirus, you know that they came out of the pets. And so these are breeding grounds for viruses. So he cultivates in flu viruses, puts them in air, and then air is guided through the material, and then he collects samples and counts how many viruses can pass through, none. Okay? And then he takes the material out and looks under different testing protocol for characterization of viruses. What they do, they basically they turn into some oily substrate, denatured. Okay? So this is a breakthrough for us, and hopefully I will be able to share with you even more detailed experimental work, maybe a couple of years down the road. So today, let me just conclude. I think by sharing with you the picture of the students. So that's our department, and these are the current students who are in my group right now, and several of them are from India. Akshata Kulkarni is from ICT, Aparna Agarwal is from ICT, Pratik Gotard is from ICT, and some from Korea, from US, Ukraine, and few are from China. And this is the older group of people whose work I presented today. Dr. Shao Wang is in Shanghai working for BASF. Dr. Andrew Sinko is working in an American company. Sanjun Kim is at Hyundai Motor, and he is now trying aerosol material as a filter material for handling air in car. He calls it antiviral filter material. So it's a sexy title. These are the agencies who funded my work. And so before I leave the stage, I want to share with you that my new responsibility in managing the 3 journals from Society of Plastics Engineers, and I particularly am editor-in-chief for Polymer Engineering Science. These are the 3 legacy journals for SPE, and all the authors who are in the audience, please submit your next paper to our journal. Thank you very much for your attention. I am on time. My name tag should be shown.